Assalamu alaikum. This is Team Don't Care Condition. Today we are going to explain our SAP 1 group project. First of all, in SAP 1 we have a lot of registers which need clock pulse to store its memories. In our clock pulse we have three inputs called auto, manual and halt, which produces auto clock pulse, manual clock pulse and halt to stop the operation on its entirety respectively, and there is one output. Inside the clock pulse subcircuit, there are two more subcircuits which produces auto and manual clock pulse. Inside the auto clock pulse subcircuit, there is a 555 timer IC which produces a square wave that represents our auto clock pulse. Inside the manual subcircuit, we have we have another 555 timer IC which produces a clock pulse that can be controlled by an outside push button. And there is an halt input, active high input, that stops the operation on its entirety, and there is a combinational logic that includes all of the three inputs and produces only one output. Then we have our program counter. There are four inputs in program counter called counter enable, counter output, reset and clock. There are three outputs called Q0, Q1, Q2. The outputs are connected to a BCD 7-segment display to better understand how the program counter counts value based on a clock pulse. Inside the program counter subcircuit, we have three JK flip-flops that acts as an asynchronous counter. There is a reset pin that is connected to all three of the JK flip-flops, so we can use it to reset our program counter and set the value to 0. The outputs of the JK flip-flops are connected to a tri-state buffer so that it can disconnect the outputs from the bus bar when all the other components are sending data to the bus bar. Memory address register or MAR is a 3-bit register that has one control bit called memory address in. It decides to store the current values of the bus into the MAR. Inside the memory address register subcircuit, there is a um, D flip-flop IC. It has 4 input that is capable of storing 4-bit data, but we only use 3 bits. And there is the control bit MI that is connected to the enable pin of the chip. Input unit is used when computer is needed to be programmed by writing data into the RAM in program state. The input switches in input unit are 6 data switches, 3 address switch and 1 read and write switch. The run in program prog selector switch decides which state our computer is in. When it is on run state, the program is in execution on the computer. Prog state dictates when some data needs to be written into our RAM before running the computer. Based on run or prog state, a 3-bit address will be selected from either MAR or input unit using the address selector. The address selector has 3 inputs coming from MAR and 3 inputs coming from input unit, and one in selector switch called run and prog, and 3 outputs. Inside the address selector, there is 3 subcircuit, all of which is connected via a run/prog selector switch. Inside one of the subcircuit, there is a combinational logic that dictates which of the inputs will be shown on the output based on the run or prog state. Arithmetic and Logic Unit or ALU is is a combinational logic circuit that is capable of 6-bit binary addition and subtraction. There are two control bits called addition slash subtraction select or SU that decides when to perform addition operation or subtraction operation, and ALU out, that is called EO. It puts all the ALU output onto the bus, and output of the ALU should be disconnected when RO is low. And ALU out, it puts all the ALU output onto the bus. There are 6 input that comes from A register and 6 inputs that come from B register, and ALU subtracts or adds these two numbers. Uh, ALU is a combinational circuit, so doesn't need a clock pulse, unlike other registers or counters we have used in SAP 1. Inside the ALU, we have two full adder. Uh, two full adder. Inside the full adder circuit, there is two IC pin that is able to add or subtract using two's complementary rule. The additional full adder circuit is used to subtract from a smaller number so that we can have a negative output. The 6 output and 2 additional output carry and sign are connected to a tri-state buffer IC so that it doesn't send output to the busbar while other submodules are working. B register is a 6-bit size register that has one control unit called B register in or BI. It stores the current value of the bus into the B register. Inside the B register, there are two D flip-flop ICs that is capable of storing 8-bit data. Mm, we use the BI pin to connect to the enable pin of the ICs. The B register is used to store values for ALU operation.
After that, we arrive at our RAM. The RAM is like the heart of our SAP1 project. If we look at the RAM, there are 6 data pins, one read and write input where write is active low, 3 address bits, one control bit, and 6 output bits. The control bit RO indicates when RO is 1, the RAM will output its data to busbar. The RAM stores data from the input unit and supplies the data to B register and A register to perform some arithmetic operation later on. If we go inside the child sheet of the RAM, we will see 274LS189, which are 64 bit if I am correct, which are sorry yes, which are 64-bit random access memory, and we used it as this can store up to uh, four, 4 data bits in each address location. We need 6 data bits, so we have divided into 2 parts, and this RAM gives us uh, active low output, so we have used NOT gates, and there is also tri-state buffer here. If we go outside our RAM, next we see the instruction register. The instruction register um, is like the here the all the instructions are provided to other components. When we give some opcodes and address location in the input unit, that those are supplied to the instruction register, and the instruction register divides them into 2 nibbles. If it's okay to say it nibble, because nibble is like 4 bits. These are 3 bits and 3 bits. The upper nibble goes to the controller sequencer, where it we will see how the control sequencer works later, and then the lower nibble goes to the busbar, and this lower nibble is the address of the instruction that will occur later on. If we go inside the instruction register, it's just simple D flip-flops, and here we can see the OE or output enable pins are active low, so we have used a NOT gate and connected the instruction pin IO. IO indicates that when it is 1 the instruction register will output, and there is also a reset pin which is connected to the enable pins. No, those are connected to the MR pins. If reset is 1, these D flip-flops will automatically go to 0. And there is also a II pin which is instruction in, which is also active low, which is connected to the enable pin, and enable pins are active low, so sorry, in instruction in is active high and enable pins are active low, so we have connected a NOT gate with the II pin. And next we go to, oh, here also here the upper nibble which is not controlled by the control bits, so we have connected the output enable pins to the ground, so it always outputs. And the lower nibbles I2 to I0 is controlled by the control bit IO, so we have connected here the control bit here, not here. That's it. Then we go to the controller sequencer. The controller sequencer controls every component of this um, SAP1 project. The control sequencer consists of a ring counter and um, some combinational logic circuits. The ring counter provides the clock pulse, the time states, and in our lab manual, if our in our lab manual we are instructed to use 6 time states, and we have also said that instructor also said us that if we can reduce the time state, that will be better. So if we see that the counter enable, when it's enabled the counter will count up. This does not need any bus bar operation. It will not send any data to the bus bar, so there is no possibility of occurring any type of clash with other data from the other component. So what we have done is merge this counter enable with the next one ROII, so we have reduced one T state like that. So our project has only 5 T states and other combination logic which will provide the control bits according to the instruction. Then we arrive at our accumulator. Our accumulator is capable of storing 8 bits. Why do we need 8 bits? Because our project is 6 bits, but when we add something, like if we see an example, if we add this 6 bit with this 6 bit, this gives us a 7 bit result. To see this 7 bit result we need the carry output, and this carry output is stored here, C out, and when we subtract a smaller number from a larger number, this will give us a negative number, and the negative sign bit is also stored in this accumulator. Our SAP1 project is capable of showing 7-bit output and also negative output with negative sign. What we have done is we have connected ALU carry out and sign to the accumulator, and the accumulator provides later to the output register. If we arrive at the output register, if we go inside, this also can store 8 bits from the accumulator, and there is also a control bit OI which indicates when it is on, the output register will take input. If we then we will arrive to the double double. The double double is not that much of a good, what we say, there is many carry propagation delay that occurs in a double double, but our project is not that much of a big project, and we use only 6 bits, so there is not much trouble in using this configuration. We have used this double double formation. The how we arrived into this circuit, the link to that video will be provided in the description. And this 7 segment displays are connected to the double double to show us the result. There is also a common anode, I believe. If we Yeah, this display will show us if there is any a negative result. It will show us a negative sign. And let's now we take an example of how this SAP1 project works. Next, let us take an example of an addition and also a subtraction. First, we need to run our Proteus file. If we run it, yes, there is error occurring because we are in auto mode, and we need to stop auto mode. Like we need to stop the clock pulse before running the Proteus file. If we run it now, as first, if we need to input something with the input unit, we need to go to the proc state, and we need to be on the read mode. Then we will select the address. We will select in 000. Then we will select the opcode, which is 000, which is the load opcode, and we'll select the address pin bit of the load instruction, which is 101. We'll remember that 101. Then we will write this in the RAM. Next we will go to the next address location. Next we will select the next opcode, which is 001, which is the adding opcode. Then we will select the address location for that adding bit, which is 110. We will also remember that. Then we will go to the next address location. Sorry, I forgot to write it. Here we go. Then we will go to the next address location. Then I will select the next opcode, which is 011. The next 3 bits doesn't matter. Still we are making them 011, which is the output opcode. Then we will write it on the RAM. Then we will go to the next opcode. Then we will select the halt opcode, which will stop the operation. Then we will write it on the RAM. Then after that we will recall our loading opcode address location, which is 0101, and we will write our first data in there. Suppose we write 101010. Okay, then I write it on the RAM. Then the adding location, which was 110, we will store our next data there. Suppose we store the same data bit, and I write it on the RAM. After that we will go to the proc state, and we will start our clock pulse and see what happens. It gives us the result 84. Let us see if our result is correct or not. 101010. Let me copy it and paste it there. I calculate. Yes, it gives us the 84 result. And here the adding operation is done like this. And then we let us take an subtraction example. First I stop this and go to stop the clock pulse. Then I run it again. Then I go to prog mode. Then I select the address location, load opcode, write it on the RAM. Then 010, this is the only change here. The 010 is the subtraction opcode. Sorry, I have made a mistake here. 000 101, I need to write it there. Then I change the go to next address location. Then I select 010. If I take a smaller number first and write it on the RAM, then I take a large number and write it on the RAM. then I go to run mode and start the clock pulse. Let us see what happens. Minus 16, if I see that it is correct or not. The first one was 1111, the second one was 1111, 5 ones. I calculate, yes, it gives us the result minus 16. So this is how the subtraction operation is done, and this concludes our presentation of our SAP1 project. We made some improvements here, like we reduced the time states, and we also made an we also made it that we can see negative numbers, we can see 7 bits output. We ran into many problems while integrating this as a whole, because it was made by different people and different components was made by different people. We ran through many trial and error, and we arrived at this result. Hope you liked it, and this concludes our presentation. Assalamu alaikum wa rahmatullah.